Good morning, everyone, and welcome to JCON Day 3. This JCON video fits perfect to my next talk, in-memory computing, the big picture. Welcome and thanks for joining. So this talk is all about in-memory computing, where we can use in-memory computing and how can in-memory computing help us to accelerate, improve our applications. So of course, for all of these modern software applications, they need fast response time, almost in-memory or real-time response time, and they have to collect and to process tons of data. So this is the reason why we need super fast application, efficient applications, and in-memory computing can help us to build such things. But not only for creating innovative software, in-memory computing is actually everywhere. So whenever a process is too slow with conventional hardware, then we try to accelerate it by keeping data in memory, caching data. So we have in-memory computing even in devices like hard disks, printers, of course, mobile devices, edge devices, and even database management systems using memory computing. They need caching internally to accelerate database development. My name is Markus Kett. I'm a CEO and co-founder of MicroStream, and I like to give you an overview about various in-memory computing solutions. And it's because I work on database technologies and on development tools for Java developers with my team for more than 15 years now. And so when we talk about in-memory computing, so I often was very confused about the different solutions, how they work, what are the differences, and so this is the reason why I like to give you an overview. Because when I ask the stupid questions, then mostly when there were more people in the room, then they thanked me that I was the guy who asked the stupid question, because mostly this is not a stupid question. Mostly we have a buzzword bingo and confusing, and so this is important to ask the stupid questions really to get the right answer. So this is why I created this talk. So I like to start with why in-memory computing, and then to search for the latency actually. So what is the reason to use in-memory computing? Because memory is still expensive, so we need really a reason for using in-memory computing to use the expensive memory. Then I like to talk a little bit about the persistence in Java. How does this work in principle? And then distributed cache, in-memory data grid, in-memory database, in-memory data processing with pure Java, and some MicroStream. And then I have a demo also. And hopefully we have some time for questions. I'm sure we have time for questions. I will stay in the chat that I can answer your questions. So why in-memory computing? Memory is still expensive, but incredibly fast, of course. When we have a look at the numbers, then we talk about nanoseconds when we have instructions, assembled instructions. They are executed in nanoseconds in memory. This is really super fast. And the closer the storage is to the CPU, the faster it is, but also the more expensive memory is. So whenever I can use in-memory or data processing in memory, then I can expect it's super fast. but there are also differences between the memory solutions. So there are really huge differences. So here we talk about factors, factor 10, factor 100, sometimes factor 1,000, and sometimes really factor 100,000x faster or slower. And this is really tremendous. So if you can accelerate your systems 1,000x, wow, go ahead. This is a big deal. Brief overview. Of course, CPU caches the fastest. We talk about nanoseconds. When we mostly talk about in-memory computing, then we mean the conventional RAM. And here we have access time in around 65 nanoseconds. Then we have persistent memory, which is actually a very interesting solution, but I don't know exactly how it works, how it goes in practice. So how often is it really used in practice? So Intel sold the complete persistent memory technology to SK Hynix some years ago, two years ago or so, for some $1 billion. I don't know, it's not because persistent memory is not efficient, or it's more like a political decision, I guess. Persistent memory is very interesting because I can get access time that is pretty close to conventional memory, but it's much cheaper, and you can store your data persistently. It's similar to a SSD, but much faster. So around 250x faster than SSD. When we have a look on Java, then with Java we are always in memory, and this is really cool, which means everything that is written in Java should be super fast because of our great JVM with the JIT compiler, just-in-time compilation. So the JIT compiler is able to translate the Java bytecode into machine code that is really executed super fast. And though there is not much difference between a Java program or a C program on a server side. So many people believe, and they are convinced, on devices, embedded devices, C is still much faster, and it's the reason why Java wins on the server side, and C mostly wins on embedded devices. But for our purposes, server-side applications, Java is really super fast, runs in the memory. Everything we can do in Java with pure Java will be super fast. All right, if Java is so super fast, where are the latencies? I think this is pretty clear. As soon as we leave the Java way, as soon as we do anything outside the JVM or the virtual machine, then suddenly the performance goes down. And of course, it's in terms of database development, we have to leave the JVM. So we store data on remote machines, and here could be some delays, might be some delays. So let's see how this works under the hood, because mostly when we talk about database operations, then the database is a black box for us. It's because we have SQL. So we send an SQL query to the database, and the database cares for the rest. Not much people are really interested what happens actually inside the database. So let's have a look inside the database. Here we can see we have business logic. Suddenly and surprisingly, business logic in the database. Most Java developers won't do that, but the database experts, they love it, and so they cannot understand why we need Java. So the Oracle developers are able to. So I have seen complete ERP systems written in PL/SQL, stored procedures, stored functions. So they have proven this works. So why actually do we need Java? Good question. It's a completely different approach, and we love object-oriented programming, right? So this is the reason it's much more powerful and so on. But it's possible. So we have tons of business logic in a database, and of course RAM, because database runs on a remote server, and here we have the database management system that cares for everything, executes your SQL, caches data in memory, so to make the database more efficient, to provide a better response time, the best possible response time. So here the fastest database will win on the market. So here also performance is super important for database vendors, and also the database internally avoids or tries to avoid hard disk access. So because access to a hard disk, we saw the numbers, is the slowest. So even network, when we talk about network inside a cloud provider, inside a data center like AWS, then network could be faster than access to a hard disk. So this is the reason why we should really avoid accessing the hard disk. Whenever it is possible, keep the data in memory, and we read the data from fast memory. All right, here also interesting is it's not really surprisingly, so everybody knows it, but for later, it's interesting that here we can see the storage data are directly on the database machine. But in the cloud, you cannot be sure that this is really the case, because perhaps your database runs on any virtual machine, and but the storage data they run on a storage machine anywhere else. So then when we access the storage, then we have network between the storage and the database server as well. And again, one more network call or traffic on a network. So we cannot be sure, so can happen. And here are the delays. Here are the latencies, network, and of course, access to the hard disk. So back to our black box. We have further latencies in database operations, and the reason for that is that Java and database systems work. They work completely different. In Java, we have objects. In relational databases, we have tables and relations, and it's not possible to store complex object graphs in flat tables. So we have various mismatches here because of the differences between Java as a programming language and the relational model. And also the in-memory model of Java works completely different from relational databases. The programming language is completely different. So in the relational model, of course, we have no inheritance. We have the object model itself is much more granular in Java, for instance. And this is the reason why we have various impedance mismatches here. So we have to fix that. So if you're lucky, then we have a software that fixes this for us, so that developers don't have to deal with this. With the modern NoSQL databases, we have actually the same challenges, and it's because they introduce a completely different data structure. but all of these data structure are also incompatible with the objects in Java and with the with the memory model of Java. So we have key value, we have column store, we have document-based JSON databases, graph databases, and object-oriented databases, time series, and so on. But all of these data structure and data models or formats are incompatible with the memory model of Java. So same problems or challenges here as well. We need some data conversion behind the scenes, and here are the latencies. So this is very important. Then even if you use a graph database, then it's not compatible with the native Java object model. So they introduced their own proprietary graph model, and it's also with object-oriented databases, by the way. So they can store objects, but this is a proprietary object model of the database, and it's in any case incompatible with the object model of Java. So we need a mapping here as well, and I think this is also the reason why the object-oriented databases they are not really popular in practice, and so this is a concept from the 1990s, and yeah, it's not relevant in practice so far. It's because of the differences and the trade-offs when we use Java. So here we can see in the architecture we need object relation mapping between the relational database and Java, our app or service, and or we need a data conversion if we use a NoSQL database. And this conversion or mapping is required through every single read and write. And this is really a delay. This is here are the latency. This is expansive latency. We have the conversions, we have network, and we have the access to hard disk. And we talk about millisecond latency. It's when we access hard disk, we talk about millisecond access time, and also object relational mapping takes mostly milliseconds. So there are various articles in the internet around impedance mismatch. Very interesting. Object relational mapping. You can find it on Wikipedia, a cool article also. Okay, back to our architecture. To accelerate database operations in Java, we are used to use a cache. So let's use a cache, and let's store the result sets in a cache. Then the next query will hit the cache and doesn't need go through the network to the database, asking the database. Database has to access the hard disk. So then we can avoid hitting the database. So we read the data directly from the cache. And this should be super fast because it's pretty close to the application. It runs within the same JVM process as your app or your microservice. And then reading from cache will be very, very fast. Here we have, it depends which format is used. For instance, Hibernate second level cache. Here we see that the objects are serialized into the cache, and here we have a delay as well, latency as well, and you also can store the objects via key value. So we have here key values data structure in a local cache. All right, then now we have two layers. We have an application layer, we have a storage layer. But in practice, mostly we build distributed applications. So which means we scale horizontally to to share the loads to numbers of instances of our application or our service. So we start multiple instances of our application, a common distributed system. Now, all of these instances have their own local cache. What happens if the data changes in the database? So let's say one node changes an object in the writes it to back to the database, then only this node in the database are consistent, and the data in all of the other nodes in their local cache are inconsistent. So this might be a problem. So we can fix that. Was not the correct slide. Now it's distributed cache. What we can do is now we can put the cache between the application nodes and the database. So then my cache runs on a remote machine. And here we can run a complete cache cluster. Then we talk about distributed cache. And now this cache is now can be connected to the local caches, and whenever you make an update in a cache, then it depends on your cache policy, on your cache configuration, how you store data in the cache. If you store the data in the cache first and then in the database, or you go around the cache and store it in the database. So there are various cache strategies, and so you have to define the cache policies. But now we hit the cache, the distributed cache, and this is how it works in general. So the architecture gets more and more complex, and actually we talk about in-memory computing and distributed cache, but here we can see the data are in memory, of course, but they are on remote machines. So we have to go through network when we read data from a distributed cache. So, and this is the reason why we have here latency as well. So it depends on your network, it depends on the traffic on the network and so on. But also when it also depends on how does the cache cluster works internally. It's because the data in the cache can be distributed, and so that here is a cache manager that has to find the data on which node will the data be. So load the data from the right node, and has to go through network internally. If the data are not in the cache, then the cache hits the database and reads the data from the database, and so on. So this is functional principle. We have here key value data structure, and examples for that are Redis, or you also can use Oracle Coherence as a distributed cache, or Hazelcast. So there are various vendors and solutions on the market, and they are really they are bulletproof. So they run, many customers use these products, and so they're really stable and really fast. So check it out. Which cache framework works best for you? So most of them are open source, and the vendors mostly provide managed cloud solutions for that. The database is still important here, because the single source of truth is still the database. But the more memory we have, the faster the application will be, the response time. It's because we can keep the data in memory. And by the way, we talk about memory computing, which means, yes, you need tons of RAM, but these distributed caches are really flexible. So you can they can automatically scale out and scale in. So you can really save infrastructure costs by these solutions. They scale automatically. In the cloud, the vendors mostly provide serverless solutions of their products, so that they really save infrastructure costs. They're very efficient. What we can do if the load gets higher, then mostly we see that we have also a database cluster. Then we have another cluster. So now we have already 3 clusters in our system. It's because the database also needs to be clustered if the load is high. And then here also we have remote machines, and the database runs on a remote machine, and we have also a network between the database replicas, of course. Right, so summary: distributed cache, mostly key value data structure. They are very flexible. They can scale horizontally through hundreds or thousands of nodes. They provide automated scale out, scale in. Mostly the vendors provide cloud solutions and serverless solutions, so to save infrastructure costs, get managed services. It's important to have high availability, and persistence is also provided by distributed caches. Either the persisted data in the relational database that's still used, or in the database cluster, or they create snapshots. So it depends. You can choose the persistence strategy of your distributed cache. They are mostly easy to use, not too much code to write. They tons of documentation on the internet. There are also some cons. Of course, there are no SQL queries because of the key value structure. So we have a NoSQL. This is NoSQL solution. All right, in-memory data grid. What actually is in-memory data grid? And I was really confused about the difference between distributed caches and in-memory data grids. It's because when you have a look on the vendor map, then most vendors of distributed caches are also vendors of in-memory data grid. So where's the difference? So here we can see in my slide, I added some business logic here. So we can now add some computing functions to our cache nodes, and then the in-memory data grids are able to execute operations, computing operations, and share it through their in-memory data grid nodes. And this is the most important difference between the distributed caches and in-memory data grids, that they can also compute something through hundreds or thousands of nodes and share the load, the computing load, through the cluster. And as I mentioned before, the architecture is pretty much the same. Of course, the particular solutions work different internally. So you should have a look on the documentation, how they work, check out the code. And when you have a look in the vendor list, then you can see there are all of these distributed, or most of the distributed cache vendors are also vendor of the in-memory data grid. So they increase their distributed cache with computing function. And we have Hazelcast here, for instance. We have Red Hat with the JBoss data grid. Coherence, and so on. Most of them, or all, they are open source, and the vendors provide fully managed cloud solutions. So you can check it out in the internet. And yeah, if you have enough load, then it can be a great solution for you. The architecture is really complex in total, but this is a common enterprise application architecture. But we have 3 layers here. We have 3 clusters. Many things to know and to learn and to test, to deploy. But common infrastructure for enterprise application, and it's really proven. Summary for in-memory data grids. Data structure is also key value. They are also very flexible in scaling horizontally through hundreds or 1,000 nodes. You have enough memory, enough money for buying this memory power. Of course, they also support similar to caches, all kind of applications, so they can really easily put your in-memory data grid or distributed cache between your application and a database, and no matter which application you run, you can use it to improve your performance. In terms of persistence, it's the same. We also need the database system as a single source of truth, but you also can use snapshots to persist the single nodes of your in-memory data grid cluster. Some of them, they have SQL support or kind of like SQL dialect, but it's, of course, we talk about NoSQL solutions. It's not the same SQL. They have not the same SQL features than as in a database, of course. And it's not surprisingly, it's because even the database systems, they have many differences between the SQL dialects. Okay. In-memory database. Next solution. What is in-memory database actually? So when we have again a look into the black box of a database, and we can see the layer here as well, the different layers. The in-memory database does not store data on disk. The in-memory database, of course, stores data in memory. The database management system runs in memory, and the data are also kept completely in memory. So which means if you run an in-memory database, you have all of your data in memory. So back to our persistence architecture slide. So let's run an in-memory database. So now we are able to run the in-memory database within the same JVM process of our application or microservice. And of course, then perhaps it's not a solution for microservices because of the startup time. So it's required to keep and to load all data in memory initially when you start the machine. And then it's more suited for monolithic applications, I would say. And then you have the database inside the memory. This will be executed very fast. It's because fully memory. And the great thing here is, of course, now you have full SQL support because it's pretty much the same database, or actually it's exactly the same database in comparison to the traditional database you run. And so this is the great advantage, that it can be a drop-in replacement, sorry, not a drop-in replacement. You can put it between the application logic and your database, and you can instantly increase your performance, and you don't have to change much about your system. So you don't have to deal with a completely new technology like in-memory data grid. So it's pretty much the same solution, and if you choose an in-memory database from the same vendor as your traditional database, then it will be pretty much the same. So this is the great thing here. But the same here again, you need memory for that. So we have to run big memory machines. Otherwise, it makes no sense to use it. Here you have the same. What if we want to run a distributed application? Does it make sense to start all of these machine instances with their own in-memory database inside? Basically, you can do that, but then we also have challenges in terms of consistency. So it's better to put the in-memory database between the application and the database used for a backup. Which means we have also the same architecture here as well. So we have here a caching layer or the in-memory database layer, and we run the in-memory database cluster between the application and our traditional database cluster. Then when we need fast access, then we hit the in-memory database. And if data changes, then it will be stored in the traditional database you run as well as a backup. Of course, all of these solutions, they require running numbers of machines. So the cost will increase, of course. You need memory and you need many machines. Deployment is effortful, of course, because you have 3 layers, you have numbers of machines. But state of the art, so the leading products here, of course, are Oracle in-memory database and SAP HANA, for instance. So these are the market leader here in this field. If you're not familiar with in-memory data grids, if you're database experts or if you're database expert teams, then and you don't want to change much about your application logic or infrastructure, then I guess it makes sense to choose an in-memory database to accelerate the performance of your system. Summary here again, the data structure here is still relational or column store mostly. This is the difference between the distributed cache and in-memory data grids. We have full SQL support. It's pretty much the same. So administration is the same. This is really cool. No changes to your existing application. So everybody who maintains database is familiar with the technology. So it's also high available. You can scale it horizontally by replication, and it's also, of course, suited for all business applications. In-memory data processing is another approach. The concept is well known for many years. So keeping data in memory and storing and creating snapshots. This is also a cool approach because I mentioned it already. Everything we do in Java is super fast because of our great JVM performance, and or when we use a microservice, we can use GraalVM native images, and so keeping data in memory can make sense, and doing everything with Java, the complete data processing. And we have a great data structure in Java. We have object graphs, and we can use all types. We can use collections. So this is actually a multi-model data structure from nature. So it combines everything, or you can combine everything that is provided by a database, where the database data structure are limited. In Java, we are not limited. We can do really everything with our object model. That's really great. So we can store simple lists if you have machine data, We also can create very complex graphs with circular references if you have many relations. So we can do everything. We have a multimodal data structure. We have a query language. We have Streams API to search and to filter on object graphs. And everything here is executed in microseconds because it's in memory. And so your Java app will be super fast. And it's everything. If anything is missing here, so you miss full text search, yeah, you can have a look on the Java ecosystem. You can use Lucene for that. So everything is here in Java and can be used. And also, if you want to work with indexes, so you can create your own index. You can do everything with collections. And when we search and work on object graphs, then it's really up to 1000x faster than traditional databases can be. This is really great. And now I would expect all of these data applications should be written in Java and pure Java. Never use a database anymore. But there might be a problem. Persistence is missing in Java. And this is the reason why we have worked many years on MicroStream, but this concept is, we have not invented this concept. Of course, there is the concept called system prevalence, documented also in, well documented in on Wikipedia. You can find an article. And here we keep the system state in memory and create snapshots of your of our object graph and store it persistently on disk. And with MicroStream now we are able to store only the deltas, so not to create a snapshot of the entire database, but only storing the changed objects. And then we have micro snapshots. We store it also as binary on disk persistently, and vice versa. We are able to load single subgraphs and restore it in memory. And this is really powerful. You can download MicroStream via Maven, and you can find the code on GitHub, so it's open source. There are also other frameworks out there. They have followed the same approach like Prevailer, but it's not further developed, and it's because there is no project out there that is so much powerful than MicroStream. We have solved all of these problems with system prevalence, so we don't create snapshots of the entire in-memory database. Only the deltas are stored. We can load subgraphs, so lazy loading. We manage class changes automatically. So this is the reason why MicroStream is a completely different approach. And it's integrated now in Project Helidon. It's also, we have a beautiful integration here, and also a beautiful integration with Micronaut, with these micro runtimes. And it's because MicroStream is so tiny, so small, that we call it micro persistence. It's a small Java library and has no dependencies and really works fantastic for microservices. And what have we done with MicroStream? So let's go back to a persistent slide with the Java application here and the database, and let's have a look again inside the black box. What we did with MicroStream is we replaced Hibernate or object-relational mapping or any data conversion with MicroStream. Okay, then a cache is not needed anymore, because now with MicroStream we work on the object graphs in memory. So we have our objects still in memory, already in memory. So we don't need a local cache anymore. Can kick it out. The architecture becomes now super simple. And on the database side, now with MicroStream, our object graph in memory is our database, our in-memory database. But it's not the in-memory database management system, so it is very important to mention. So it's the database, here are the data, but there is no management system that cares for operations on your data. So you have to care for the operation, all operations on your data, validation and so on. We care anyway in Java. We care anyway for validation and for concurrency. So we have functionality in Java to do that. On the database side, we need the database here on the database remote server. We need that database in memory, not really, because we only store the data in binaries on a disk. So we kick out the database system on the remote server, and now we only have in-memory database. That's a single source of truth, and we only have a storage where we store the binary files. That's it, no more else. We can store data also in database systems or in S3, for instance, in a blob store. That's possible, but the functional principle works also with plain files. And here is then the architecture, and looks really, really simple, and is really simple. And there are no more conversion or no more object-relational mappings between the app and the database. So we eliminate all of these latencies. And then we have our blob store. Then let's compare it with the cluster architecture. Now we replace our application cluster with MicroStream node. So it's super powerful. Perhaps you can replace an entire cluster with one MicroStream node, and it's not the MicroStream node. Actually, it's a Java node. So the JVM is the power comes from the JVM. MicroStream only stores the objects, and then we don't need the database cluster anymore. So we can kick it out. So we only need the storage. And as I mentioned, we don't need a cache anymore because we have the data already in memory. We can also kick the cache out. So then our architecture gets super, super simple. But what's about distributed applications? This was not possible so far with MicroStream. It was a single node storage, but now it's possible. Now we are able to distribute the object graph, and we can start multiple machines, multiple MicroStream machines, and the data will be replicated between the object graphs. And now we have a distributed object graph. And it's similar to in-memory data grid or a distributed cache. They introduce key value, but here with MicroStream, you have a natural, pure Java object graph. And this is where the power comes from, because now everything is in memory in your application node. It's super fast and executed in microseconds. So we can also store then data in persistent memory. If you even want to accelerate the system, then we can store data in persistent memory. And this is also fantastic because it's much faster than storing data in disk. And you can here then we have the architecture overview with persistent memory. All right, everything is open source. You can check it out. It's completely free to use, and with MicroStream cluster, then you get the benefit is you get a distributed application out of the box with the MicroStream cluster. This is the difference. So you cluster your application automatically, and the MicroStream cluster provides you application cluster or microservice cluster automatically. So don't have to care for clustering your application logic or your microservice logic. It's done by the MicroStream cluster from the out of the box. High availability, of course, load balancing, and auto scale and auto scale in. Scale out, scale in is also provided, so that you can really save tons of cloud costs. We will provide a MicroStream Cloud service. Then you can create a cluster with only some mouse clicks. So you don't have to deal with all this DevOps stuff. Don't have to care about that. So in comparison, traditional cluster, MicroStream cluster, you can really save tons of infrastructure costs, and you get out incredible performance. It's not just like a research project or so. This works in practice already. So at Allianz, for Allianz in Munich, we built various applications run on MicroStream, also for Frogport and so on. You can check it out and download it for free. So I think this was a brief overview about in-memory solutions, and when you have enough memory and enough budget, use it. So in-memory data grids, distributed caches are great solutions. They work with Java beautiful, so you can use it for all applications. And if you like the MicroStream approach, check it out, find what fits best for you. And if you have any questions, you can follow me on Twitter, or you can also enroll for a course. Tomorrow we have 3 hours MicroStream course getting started, and you can also enroll for a free MicroStream training. Thanks for joining. If you have some questions, I will stay here and answer the question in the chat. Thanks for having me. Have a great day.
Yes, thank you very much, Markus. I think there's one question. Did you see it in the chat? Have you answered?
Not yet, sorry. The relational database have security tools to protect persistent data, plus support concurrent transactions. What about the MicroStream? Yes, of course. So the database of database systems, they provide all of that. Security, we don't care for that. In our cluster, we do. The MicroStream embedded engine does not care for security. It's also not true. We have the most secure serialization on the market, so we don't use Java serialization for that. But actually, the provider cares for all security of your data, and because MicroStream out of the box is just a Java library, and it's not the database system. But the stores executed by MicroStream, the store objects, they are transaction safe. But it's not the same as a transaction in a relational database. It's an atomic all or nothing operation, so we can say it's transaction safe. And security is provided by our cluster, of course, but MicroStream open source is just the Java library. Yeah, it stores data in memory, but it connects to network to store binary in S3. That's true. So as soon as the only possibility to avoid network would be storing data in persistent memory. So if you want to persist data, then we have to go at least over the bus. Or internal network, wherever your storage is, and to store data persistently on disk. But this is the slowest part of MicroStream, of course, when you go over the network, the I/O process. But it's parallelized, so the more CPUs you run, the more channels you can use for I/O operations, and they're super fast in comparison to a relational database, I would say. And it's because there is not much difference between the speed of your the performance of your hard disk and the write or read performance of MicroStream. But we cannot avoid this, so this is physics.